About 2 weeks ago, we did a paper from the JARC wrote called Meta-Labeling Theory and Framework. And as I mentioned, this is going to be the follow-up paper to that. We explore different architectures and ways that you can actually use meta-labeling to specifically cater to the strategy that you had in mind. The idea comes basically from looking at neural networks. So neural networks have all these different architectures that one can use to solve specific problems. For example, you have artificial neural networks for pattern recognition problems. Then you have recurrent neural networks, such as the long short-term memory architecture. And then, for example, also convolutional neural networks that are often used in image classification. So what we wanted to do is we wanted to establish such architectures for meta-labeling that can, serve as a guide for practitioners to use, and as well as for academics that want to look at, want to expand on these ideas. So it's more of a theoretical paper than necessarily doing the experiments, but we'll get to it later. I believe Dennis has tested 2 of these architectures, so he can maybe give you some insight on that. And also some great news, it was published this week in the Journal of Financial Data Science. And to brag a bit, it was also the lead article, which we are all very proud of. So the authors are myself, Jacques Hubert, and Messias Alpheus, who is a senior lecturer at the University of Stellenbosch. Okay, great. So first we're just going to talk about the aim of the paper, what we wanted to achieve, and what are the goals that we had in mind. Then also we're going to talk about the separation of side and size and why it can be useful to separate these 2 facets of the model of the investment process rather than using them in one overcomplicated model. Then we're just going to review some concepts of meta-labeling and specifically how they relate to the work that we are going to do. And also then we're going to talk about model architecture, and we're going to lend a few ideas from ensemble techniques that we can use to apply to the meta-labeling architectures. And then finally, we are going to talk about the actual architectures that we established. Okay, so the first aim of the paper was to develop sophisticated strategy structures through meta-labeling. So Professor Marcus Lopes de Prado had this idea that when you separate side and size, you can have all these different strategy structures or architectures where the different components interact with each other, and then you can get quite complicated architectures, but each specific instance of that architecture is to model for account for a certain aspect of it rather than combining everything into one model. What we wanted to do also is establish theoretical principles for building an architecture so that anybody that wants to build future architectures can look at this and look at our ideas and maybe build them on their own. And then lastly, we wanted to establish various architectures that we think are promising, that one can use, and then, that other people can also use and build on these ideas. So important thing is the separation of side and size. So in the Prado's article, the top 10 reasons most machine learning funds fail, I think it's pitfall number 6. He said that when you try to model both components together, it overcomplicates things and there can be a lot of errors in it and you can make suboptimal trading decisions. So he argued that the position side decision is a purely fundamental one. It aims to capture the fair value of a security under a specific set of circumstances. So that would be basically just in a classification sense, we can go long, or we can short, or we don't take a position. So that's more or less what the position side is about, just finding the direction to trading. Then the second part of the investment process is deciding on the position size that we want to use. So position size decision is more of a risk management decision that you have to make. So, in general, if you have larger position sizes, your exposure is going to be larger and you might get greater returns, but you come at the risk of, maybe having a big drawdown as well. And then, yeah, as we previously mentioned, building one model to account for both introduces unwarranted model complexity. So if you take a look at the deep momentum network that we covered previously, they do both these decisions in the same function, right? So they optimize for the Sharpe ratio, and they use this volatility scaling within the Sharpe ratio, or with the returns, and then they optimize for the Sharpe ratio. So it's kind of like the risk management tool in this case is built into the model. And me and Michelle have been working a bit on building actually the deep momentum network. And it looks promising as well. We have to tweak it a bit. But one thing that we are going to try is actually taking out those volatility targeting or volatility scaling returns, and rather than optimize for them in the Sharpe ratio, optimize for just the classification and then take them outside, after the fact, and use that to manage the risk. And it's really interesting to see the results. I personally think this is a better approach, just because it's also more understandable what is going on, right? If you have one model and it just spits out the answer, you don't necessarily know what's actually going on. Now, if you separate the side and size, the way you can use this, a model you can build to account for this, is through meta labeling, right? And again, the Prado defined meta labeling as a secondary machine learning model that learns how to use a primary exogenous model. Later, when we get to the architecture, I'll explain it a bit more in detail, but the basic idea is that you have a primary model that decides the side to trade. Then you have a secondary model where the target variables are whether the trade was profitable or not. So when the model actually would filter out some of the trades that are false positives, so it would reduce recall, but increase precision and ultimately lead to a higher F1 score that leads to a higher Sharpe ratio. And there are three main benefits of applying meta labeling. The first is the information advantage. This is when the secondary model, is better able to utilize information than the primary model. So an example of this is in the previous paper that Jock used is he simulated an AR3 process to forecast the next day's return. So it takes in the three previous days' return, and the primary model only used the previous day's return to indicate whether you should go long or short. And then the secondary model incorporated the previous 3 days' returns. So it was better able to utilize that information. And the way you can just check if there's an information advantage is simply to build a machine learning model and see if it outperforms your primary model. The second component is modeling for false positives. That's when you include evaluation statistics from the primary model. This could be, if it's a binary classification, for example, the rolling log loss, or the usual metrics derived from the confusion matrix. And then the second part of that is including market state and regime related features. So in general, I think most trading strategies don't work in every type of market condition that there is. So you can include market state, which we define as short to intermediate term conditions, for example, or you can include regime related features, which are when there's more kind of a structural change in the market conditions. And then lastly, the secondary model produces a model confidence in whether the trade was profitable or not, and you can use this model output to size positions. Now we're actually also writing a paper on this, and if we have time, we can maybe look at this. But we basically calibrate the model output using some calibration methods that are closer to true posterior probabilities, and then we use these probabilities to size the positions. So let me first pause here. Is there anybody that would maybe like to ask a question on this? Okay, can maybe just give me a thumbs up if everyone's good. So
good, thanks, Michal.
Okay, great. So basically, our machine or the meta labeling architectures lend a lot from ensemble architectures. Though it's not exactly the same, ensemble architectures don't have restriction on the target variable, where for meta labeling, the target variables are always the values, whether 0, 1, whether the trade was actually profitable. So the architecture describes the overall approach to the problem, whereas a model is just one piece of the architecture. Now, there are three pillars of ensemble architectures. The first one is the data selection for each of the members, right? How are we going to select the data to feed into each member? The second one is the criteria for selecting members. What types of models do we want? What is the relationship we think to the feature space that we want? And then finally, there's a schematic of the interaction between all these different models to produce a final output. And the final decision is often based simply on majority voting or some type of weighting mechanism. And also, ensemble techniques are generally deployed in one of two general contexts. First one is classifier selection, where you subdivide the feature space into different regions, and that classifier for a certain space becomes like a local expert in the space that it's trained on. Then when you want the final output, there would be some distance metric from the new inputs that you have to the inputs that was trained, and you make your decision with that. And the other one is classifier fusion, where the different models are trained on the entire data set. And then also you would, combine these to get a final output. So now we've gone through all the theory, more or less, and we can get now into the specific architectures that we proposed. So a way that we thought about going when we developed these was either through a feature-driven or strategy-driven approach. So the feature-driven approach looks at the way the information is structured and how we can separate or combine the information to extract the most amount of information that the model can use. While a strategy-driven approach specifically looks at unique characteristics of the strategy that you can incorporate in the ultimate architecture. So we built each architecture to account for specific aspects. Some would focus on the evaluation statistics, others focus on the market state and regime-related features. And then finally, we wanted these architectures to serve as a guideline for people to use, and as well as expand on the ideas. So let's take a look at, this is the primary model architecture. This is a machine learning example, but the primary model can basically be any type of model that you want. It could be an econometric equation, it can be fundamental analysis, or just discretionary trading rules. So here in this example, we would have the input data, X in here, going to the primary model. Then we would have an output between 0 and 1 if you include short positions. And also the model then produces some evaluation data. And then finally, we have a recall check. If it's above a certain threshold, then you would go long. If it's below a certain threshold, then you would go short. And as in between, you wouldn't take a position. And then finally, we just have these labels then. And again, the primary model only actually goes for the side to trade. And and then the secondary model is going to allow for a new mechanism to also determine the position size, as well as filter out for false positives. Just give me a sec. I think there's somebody I just want to allow in. Okay, great. It really depends on the model that you want, but the important thing is to note you can use meta labeling basically with any type of strategy that you want to incorporate. Now, the secondary model takes the output from the primary model, which is, for example, now that's between 0 and 1, or it can just filter out the trades if it's just going long or short, and we don't have necessarily the model confidence or output. And then we have market state and regime data, evaluation data, and the normal input data. This all goes into the secondary model, and then the secondary model aims to go for, model for the target variable, which is whether the trade was profitable or not. So this is actually be between 0 and 1. Small mistake here, since we wanted to interpret as a probability because it's going to give us an inherent idea of the risk associated with that specific trade. Now, doing that is a lot more difficult than one would actually anticipate it to be. And then once you get this, estimated probability or model confidence, you can feed it into a bet sizing algorithm that produces a final output. In the paper that we used, we looked at all kinds of different bet sizing algorithms. We looked at all or nothing approach. It's basically this one where there's a threshold check, and then you would either go all in or not, or you can maybe size according to the model confidence, how confident the model is. Then you can size positions according to that. In the previous paper that Jacques wrote on the theory and framework, he used a cumulative distribution function, empirical cumulative distribution function that you train on the training data, and then you apply it to the test data. And the idea is that low position sizes, or that don't frequently occur, would be filtered out. Well, if you have a high position size, you would give a larger position size to that. And the selection of the model will depend on the data and the primary model. What's the relationship between the two? And as we mentioned, M3 can be any bet sizing algorithm from estimated probabilities. So now we get to the interesting part. This is the architectures that we proposed. So the first one we're going to look at is the discrete long and short architectures. And the idea was that if features driving a short position or a long position are fundamentally different, then you should fit models specific to those labels. So this one's developed from a strategy-driven approach, since it includes it's specific to the strategy or the shorting and going long. Even if it's a very common feature, it's just a way of thinking about going it. So again, we have the primary model. It gives an initial output. Dependent on the recall check, if you go long and short, you would then have a secondary model for the long positions and a secondary model for the short positions. And this is kind of the principle of divide and conquer. So you want one model to specifically account for how those features relate to the target variable. And we're going to see this themed throughout the paper, where if you just take one model to do everything, then it's most likely that the model is going to underfit because it can't distinguish between the features correctly and its relationship to the target variable. And an example of this is when features driving a panic sell-off might be different those from a long position. One way that you can use this is to use, for example, VPIN, or volume synchronized probability of informed trading. That's going to indicate that volatility is going to increase. And along with that, you can use other certain features to maybe indicate that the market crash is going to come. And then you would rather fit a model to those specific positions. Then the next one is the sequential architecture. So that's what we've talked about, how to use evaluation statistics, but we haven't really incorporated them, and this is taking one step further. The basic idea of the sequential architecture is that you would sequentially feed secondary models into each other and produce a final output. This introduces model variance, right? So if the data is in a linear way related, then you can maybe logistic regression. But if there's some non-linear transformations, then you can feed that into maybe a decision tree. And models use features in different ways. So it's always if maybe the features related to the target variable are linear in some instances, but then something, the conditions kind of change and there's some non-linear interaction effects, and then the secondary model can pick up on this. Another way that this can use is also to evaluate how well the secondaries model is going. So you would include the evaluation data of the 1/1ith secondary model and give it into the second secondary model, and you can repeat this process. Also, one of the things that we thought about is maybe, since recall or the number of trades that you take when applying meta labeling will always be lower, the secondary model can make sure that you're not excluding too many missed opportunities that you actually may have been profitable that you are not taking. So this was kind of the idea of sequential architecture. It lends a lot to boosting, which is another architecture that we'll get to in a second. So this one, I think personally, is the most promising one. It's called regime conditional architecture, or the broader one is basically just a conditional architecture. So the idea is, if you have, for example, a short volatility strategy, then during normal market conditions, you would likely be profitable. But if volatility spikes, if it's a high market distress and there's high volatility, the strategy probably won't perform well, right? And the idea is that you want to separate again these models into different sets of the feature space, that you can specifically model the interaction between them. And the way we wanted, I thought initially, to do it is with different regimes. So maybe there's an inflationary regimes, and then the features would interact differently with each other. Maybe there's just a normal market conditions, and then it also have a specific way it interacts, or there can be a market distress, and and the features just go wild, with the relationship where the normal structure is kind of broken. So we proposed, modeling each of these spaces separately. I think one drawback maybe of this is that if you separate it into all these regions, there maybe not enough data points to actually get a good fit. So that is a bit of a concern, but I think this is quite a promising architecture actually to use. So just looking at the schematic, again, we have the input data going to the primary model, and then dependent on the number of conditions that you have where you want to separate the space into each other, you would get, for example, this outputs basically based on regime 1 up till regime n, and then you would have input data conditioned on regime 1 plus specific market state and regime data only related to that regime that you can include, and that can go into this secondary model. Now, there are different types of regime detection techniques. Through my research, I come across directional change, which looks like quite a promising one. Then there's also, you can understand from Duke now, he uses random forests, and the hedge fund 2 sigma uses Gaussian mixture models to fit to specific regimes. So yeah, there's a lot of different types of techniques out there that you can actually use, and then with this architecture. Then we also thought about ensemble architectures. So the two that we just built was the bagging and boosting. So bagging works basically by fitting several homogeneous secondary models, each to a subsample, or a bootstrap sample of the feature space, and then you would get all these different secondary models, and then you can either through majority weight voting or some weighting mechanism determine the final decision function. Well, with boosting, you give in like the feature space, the first model takes it, and when the model maybe didn't perform well on a certain observations, it gives more weights into the next model, and then finally it goes through the system dependent on how many secondary models you want, and then it goes into the final function also through majority weighting or some weighting function. Now, bagging solves the problem of overfitting, while boosting offers a solution to underfitting, and therefore one could argue that bagging is more suitable for financial applications because in general, the signal to noise ratio is very poor. We have quite a big concern with overfitting, and as bagging addresses it, it may be more suitable to financial applications. But yeah, I think Dennis, you implemented some of these, right? And also made a new one with stacking.
Yes, exactly. So, as Micha already said, there was a first paper by Jacques where he introduced meter labeling, or said like a landmark and paper, and then Micha introduced some of the architectures, and we wrote another paper where we basically tried to develop a framework on how to select models for ensemble meter labeling. And yeah, we basically developed a 5-step framework. So the first step is where you have to choose an ensemble selection technique and method. So as Micha already said, you have like basically 4 different approaches to ensemble learning. The first, so like there's sequential ensembles like boosting. Then you have parallel ensembles like bagging, and you have homogeneous ensembles where like you have same base learners. So for example, like in boosting or bagging, if you have a random forest, you have decision trees. So those are like homogeneous learners, whereas you can also have heterogeneous learners. That would be, for example, combining a support vector classifier, a neural network, any naive Bayes classifiers, so like distinct different models. And then in the second step, you have to select an ensemble creation algorithm. So for example, like bagging or boosting are one of those, like for these specific applications. And yeah, like in the third step, you apply like a classifier combination strategy. So like Micha already mentioned, there are like weighting functions or majority voting functions, but you have like a different, like in general, there are 2 different approaches. Like one of like, so like the ones that Micha codes for are like static ensembles, where you select your models in the beginning, and then you like have at the end, like where you have the blue or like the light blue box, there's like a decision function or like a weighting scheme. But then also like I think Micha mentioned at the very beginning that you can select your ensembles based on the feature space, so like for each sample. And this is called dynamic selection, where you look at the neighborhood and look at like, so like based on this sample, like in the previous sample, this classifier or this like baseline proved to be very well, so we choose this one. And yeah, like, and then you have to define a selection criteria. So in general, you want to have, so like there are two main reasons to use ensemble learning. The first one is diversity, but you want to have as diverse learners as possible to cover all of the feature space. And the second criteria is accuracy. So you want your base learners to be better as like random guessing. And then finally you have to evaluate your ensembles, and obviously they're like the standard like classification metrics like precision, recall, F1 score. But on top of that, like for meter labeling, you should incorporate some strategy metrics as well, like the Sharpe ratio or maximum drawdown. Yeah, like that's it.
Okay, great, thanks. Yeah, that sounds very interesting. I believe your paper is almost also finished, right? And you're going to submit it one day.
Yeah, like we hope to submit it soon.
Okay, great. Thanks, Dennis. And then the final architecture that we used is called inverse meta labeling. So the problem with maybe using meta labeling is when you use it on strategies that don't have a high recall, which means that they don't produce a lot of trades. And if you filter out those trades, then you maybe will be left with too many or too few trades. So we thought, okay, how can we actually account for that? Because meta labeling only filters out trades, it doesn't produce any new trades. So I read a paper on engineering where they have like these structures and properties. And what they did was they inversed the process to find actually better relationships between property characteristics and the ultimate structure. Yeah, and that I thought that was quite interesting. So we tried to apply it in a meta labeling. So what we would do here, we would first fit a secondary model that we don't necessarily care about the prediction power, but we rather want to use it as feature importance. So what we define inverse meta labeling is as the process of using feature importance to build new theories and ideas. So yeah, we would have the primary model going into the secondary model. And again, we have all the usual data that we feed into the secondary model. And then we would decide on some important features. Maybe we have some technical trading rules that we see, oh, okay, it's actually a bit related a bit differently to what we initially thought our primary model was doing. And then you can build kind of these new ideas. Maybe the recall was too stringent. So, you know, the threshold made that there were too few trades and the recall was too low. So you want to increase recall. And then you would fit another secondary model, which you're actually going to use to filter out the trades for false positives and use the information advantage as well as then for position sizing. So this is more like, I think, a feature importance technique or something that you can actually use to also understand your models. We use the example of you can fit a random forest as your first one. For example, if you want to maybe detect a hypothetical relationship between the VIX, you know, and the one-day SPY return, and yeah, see how they relate to your actual model. And yeah, I think this is also a very interesting idea that I would really like someone to apply a bit and see if it really can help one understand one's model a bit better, and then well, ultimately increase returns and lower risk as well. Okay, great. Thanks everyone for joining. This was Liz. Is there maybe any questions that anyone would like to have before I stop the recording? Okay, let me also ask then, we also did a paper on the position sizing and calibration. If maybe anyone is interested in me just going quickly over that, and so you get kind of a feel for the whole process, how you can actually apply this.
Yes, that would be good. I would like that. Thanks, Michael.
Okay, great. You just stop my screen quickly. Okay, great. So this paper is by Ilya Borgi. He worked here at Hudson Thames. He's currently working now at IDEA, and it was also by Jock. And then lastly, I'm the last author. I just basically did make sure everything looks correct and that the graphs are nice. And so we thought, okay, how can we actually use? See, they didn't render that well. But basically, the idea is that if you have machine learning models, they don't necessarily have well predicted probabilities. You can interpret them as model confidence, how confident the model, but they're not true predicted probabilities. If you, for example, have a probability of 20% that you correctly classified, you would expect on average that only 20% of those classifications are correct. However, there's a great paper called predicting good probabilities with supervised learning, where they show the characteristic distortions that certain machine learning models display. For example, I think support vector machines push the probabilities more away from 0 and 1, while neural networks, for example, actually offer well predicted probabilities. And then there are these different calibration methods where you can bring them closer to actual probabilities. And one is using isotonic regression, and the other one is flat scaling. So isotonic regression just means it's a monotonically increasing function that you employ with just regression, and then you calibrate it closer to the true values. While flat scaling, you use a sigmoid transformation to actually also calibrate the probabilities a bit better. Right, so here's just an example of the outputs as well and how they are displayed. So we see that, for example, SVM have this kind of like normal distribution, I would say a bit. And then if you apply some isotonic or sigmoid, it gives it more bit of elongated probabilities. So let me just quickly go through some of the methods that we used as well. So this is missing. It's a working paper still. I think it's the old version. So basically, you can use the model confidence, right, to actually size the positions. And we found that with calibration, model confidence and the all or nothing approach works really well, as well as the normal cumulative distribution function. This is a technique also proposed by Prado. And these methods are fixed position sizing methods. And when you apply calibration to them, it actually works quite well in increasing the SAR ratio, as well as reducing some other metrics such as the maximum drawdown. Then you have linear scaling, where you just use min-max scaling on the probabilities. And then I quickly mentioned this as well, the empirical cumulative distribution functions, where you fit it on the training set and then use it on the test set when you're actually then trading. And lastly, this is kind of a new technique. It was invented by Ilya, and the idea is that you use a sigmoid transformation as well to actually size the positions. So from our results, we found that basically these two methods work quite well. And if you want to call all out, you can use the all or nothing approach, and to maximize returns, but it has significant drawdowns as well as a lot of variance.